Blue light suppresses melatonin, elevates cortisol, shifts the nervous system towards sympathetic dominance, and delays sleep onset. Measured, replicated, and cited in every sleep hygiene guideline published in the last decade. Avoid blue light in the evening. The screens, the LEDs, the overhead fixtures, all producing the wavelength that tells the brain the sun is still up. An optometric tradition dating back a century, with measurable heart rate variability data to support it, claims that looking through blue-tinted lenses for 10 to 20 minutes activates the parasympathetic nervous system, reduces heart rate, and calms the body down. Both claims have evidence, both involve blue, both cannot operate through the same pathway, unless the eye is two devices, rods and cones. The visual system you learned about in school, light enters the eye, hits the retina, three cone types fire in proportion to the wavelength arriving at each one. Short wavelength cones respond most strongly to blue, medium cones to green, long cones to red. Signals travel through the lateral geniculate nucleus of the thalamus to the visual cortex at the back of the skull, where the brain assembles them into the image you perceive. Color is a construction, your visual cortex building a perceptual event from cone ratios. What you experience as the blue sky or the red apple is assembled deep inside the brain from the relative firing rates of three receptor types, each tuned to a different portion of the spectrum. This system produces seeing, images, faces, text on a page, the color of the shirt you chose this morning. But the visual cortex does not keep the color information to itself. It projects to the limbic system, the amygdala, the insula, the orbitofrontal cortex, structures that regulate emotional state and autonomic tone. Color arrives at the visual cortex as wavelength ratios from the cones. Color leaves the visual cortex as a signal the limbic structures read and respond to. That projection is architecturally heavy, with dense reciprocal connections between visual processing areas and emotional regulation centers. The amygdala receives color-processed visual input and adjusts autonomic output through its projections to the hypothalamus and the brainstem centers governing sympathetic and parasympathetic balance. Red increases measurable arousal markers, blue decreases them. The autonomic shift begins within seconds of color exposure, before you have formed an opinion about the color or its meaning. Biology responds before psychology arrives. Think of a building with two separate electrical systems running through its walls. One is the power grid. It measures total energy load and adjusts the generators. The other is the fire alarm. It reads the quality of what is in the air and triggers a specific response. Same building, same wiring conduit. Two independent systems reading different properties of one environment and producing different outputs. Your eye operates on this principle. One system reads the quantity of blue photon energy. The other reads the perceptual quality of blue in the visual field. Same organ, same photons entering the pupil, two separate networks extracting different information and sending it to different destinations. Prior discussions have described how distance viewing through the image-forming system shifts autonomic balance. The visual cortex's focal to panoramic mode change, releasing the sympathetic activation that close-range processing maintains. Color perception operates through similar cortical to limbic projections. Whether the autonomic effects of color are strong enough, specific enough, and fast enough to explain what the blue glasses practitioners observe is where the physics shifts from established to emerging. The image-forming system is only half the retina's architecture. What sits behind it, and what does it do with blue? Well, behind the rods and cones, layered beneath the cells that produce vision, sits a population of cells that textbooks did not mention until 2002. A new class of retinal cell was discovered that year, containing a pigment called melanopsin with peak sensitivity at 480 nanometers, as Burson and colleagues reported at Brown University in Science. Intrinsically photosensitive retinal ganglion cells, IPRGCs, containing their own photopigment capable of responding to light without input from rods or cones. They fire independently, and they do not send their signals to the visual cortex. You do not perceive their activation as sight. They project along a dedicated neural tract, the retinohypothalamic tract, directly to the suprachiasmatic nucleus, the master clock. Melanopsin does not see. Familiar ground, the melanopsin pathway, the retinohypothalamic tract, the suprachiasmatic nucleus, the melatonin suppression signal, the circadian entrainment that requires 1000 to 2000 lux while indoor lighting delivers 100 to 500. What this section adds is the dimension that makes the paradox visible, what melanopsin responds to and what it ignores. Melanopsin responds to photon quantity and wavelength, raw electromagnetic energy, peak sensitivity at 480 nanometers in the deep blue portion of the visible spectrum, with a broad absorption curve from approximately 450 to 520 nanometers. When enough photons at the target wavelength hit the melanopsin molecules, the IPAR-GCs fire and propagate a signal to the suprachiasmatic nucleus carrying a single message, daytime. The SCN responds across multiple systems simultaneously. Suppress melatonin production at the pineal gland, elevate cortisol through the HPA axis, activate sympathetic tone across the autonomic nervous system, raise core body temperature, the hypothalamic thermostat, constrict the pupils through the olivary pretectal nucleus, a coordinated program that melanopsin triggers through one signal arriving at one destination. Every system that shifts between daytime and nighttime physiology receives its timing instruction from this single pathway. Return to the building analogy. The power grid measures total kilowatt load on the system. It does not care whether the electricity is powering a heater or a refrigerator. It reads raw energy and adjusts the generators accordingly. Melanopsin operates identically. It measures raw photon energy at its target wavelength and adjusts the body's timing systems accordingly. It does not care whether the photons arrive from the sun, a screen, or a blue-tinted lens. It reads quantity without interpreting meaning. The fire alarm, by contrast, reads the quality of what is in the air. Smoke from burning food triggers a different response than smoke from a candle. The alarm reads meaning, not just presence. The image-forming visual system reads color similarly. It interprets what the photons represent in the visual scene, not just how many arrived. Calibration target, the sun. Outdoor daylight delivers 10,000 to 100,000 lux, the intensity at which melanopsin fires at full capacity. Indoor lighting delivers 100 to 500 lux, an order of magnitude below the threshold for robust signaling. Your body receives a dim daytime signal all day and a dim daytime signal all evening, and the circadian system drifts in a perpetual twilight that modern architecture imposes. Screens at 11 p.m. compound the drift. LED displays emit a spectral peak at approximately 450 nanometers within melanopsin's absorption curve. At close range, a phone at 30 centimeters or a tablet at 40, the photon density reaching the retina measurably suppresses melatonin and delays sleep onset. Your body reads the screen's emission as residual daylight and adjusts its clock accordingly. Age adds a dimension the younger viewer does not experience. Your crystalline lens yellows progressively across decades, accumulating chromophores that preferentially absorb short wavelength light. By 60, the lens transmits significantly less blue than it did at 20. Melanopsin receives fewer photons at its peak wavelength from an identical outdoor environment. Sleep fragmentation, early waking, afternoon fatigue, partly a consequence of this optical filtering, the lens changing the photon input before any neural processing occurs. Lens yellowing affects the image-forming system differently. The cones adapt through color constancy, the visual cortex's ability to perceive colors as stable despite changing illumination. A 65-year-old perceives blue as blue despite the yellowed lens filtering some blue photons before they reach the cones. The perceptual system compensates in a way the melanopsin system cannot, because melanopsin measures raw photon energy without cortical processing, and there is no compensation mechanism for a signal that never reaches the receptor. Two pathways aging differently inside one eye, the energy measuring system losing sensitivity to blue, while the perception measuring system maintains its blue response through cortical adaptation. The paradox between the two pathways may actually widen with age, the melanopsin pathway weakening decade by decade while the perceptual pathway holds, making the relative contribution of color perception to autonomic tone larger in the older eye than in the younger one. The viewer over 60 who finds blue-tinted environments calming may be experiencing a perceptual pathway that has become the dominant autonomic input precisely because the melanopsin pathway has weakened beneath it. Pathway 1. The pathway every article about blue light describes. The physics is clean and the evidence is established. Amber-tinted lenses worn for 3 hours before bed measurably increased melatonin onset and improved subjective sleep quality, as Schechter and colleagues confirmed in the Journal of Psychiatric Research. Amber lenses block the emission band, preventing those photons from reaching the melanopsin cells. Melatonin rises on schedule. Multiple independent trials, randomized and controlled, with both subjective reports and objective physiological markers showing improvement. That data, the convergence of melanopsin physiology and amber lens randomized controlled trials, is why I wore amber lenses every evening for 30 days, tracked the shift in sleep onset latency, and did not go back. Now, Pathway 1 explains why blue light at night is activating. It does not explain why blue-tinted glasses during the day appear to be calming. Melanopsin responds to raw photon energy. Blue-tinted glasses do not increase the photon count at melanopsin's peak wavelength hitting the retina. They filter the visual field, changing what the world looks like without changing the photon energy reaching the melanopsin cells. Ambient light passing through a blue lens still contains mixed wavelengths at mixed intensities. Melanopsin receives approximately an unchanged photon input with or without the glasses. If the calming effect is real, it operates through a system melanopsin does not use. What pathway calms when the known pathway activates? You may recognize this gap from your own experience. You followed the blue light advice, installed the screen filters, dimmed the evening lights, bought the amber glasses, and the sleep improved somewhat. But the afternoon anxiety did not change. Stress during the workday did not shift. The restless feeling at 3 p.m., the tension accumulating between the shoulder blades by 5, the difficulty settling the mind after dinner even though the screens are off, none of it responded to melanopsin-based interventions because none of it operates through the melanopsin pathway. The clock was corrected, but the autonomic tone was not, and Pathway 1 was addressed. Pathway 2 was never part of the conversation. The question shifts. How does a blue-shifted visual field calm the nervous system through an eye that uses blue to activate it? Return to the image-forming system. Your limbic system reads the color signal from the visual cortex and adjusts autonomic output before you have formed an opinion about the color of the walls. Red environments elevate heart rate and skin conductance. Blue environments lower them, measured through HRV, galvanic skin response, and cortisol sampling, not self-report. The effect operates below conscious awareness. The autonomic nervous system shifts in response to color composition before the prefrontal cortex has processed the visual scene as a color name. The limbic system does not wait for the word blue to form in your mind. It reads the signal from the visual cortex directly, and the autonomic adjustment is underway within seconds. This pathway is anatomically distinct from melanopsin's route. Cone signals travel from the retina through the lateral geniculate nucleus to the visual cortex, area V1 then V4 for color processing, and the visual cortex projects to the limbic system through well-mapped corticolimbic projections. The amygdala receives color-weighted signals and adjusts autonomic output through its connections to the hypothalamus and brainstem autonomic centers. Wavelength-dependent modulation of brain responses, including limbic activation patterns that differ by color, was measured directly using functional brain imaging, as Van de Waal and colleagues demonstrated in proceedings of the National Academy of Sciences. Blue-enriched light produced stronger activation in limbic and thalamic structures than did green light of equal intensity. The brain's emotional and autonomic centers responded differently to different wavelengths of equal brightness, confirming that color, not just intensity, modulates the limbic autonomic pathway through image-forming visual processing. And then, the hypothesis. Blue-tinted glasses change color processing in the image-forming system without significantly changing the photon energy reaching melanopsin. Your cones register a blue-shifted visual field. Your visual cortex processes the color through area V4. The limbic projections, amygdala, insula, orbitofrontal cortex, receive the blue signal. The autonomic response shifts toward parasympathetic dominance through the geniculostriate limbic route, a completely different neural pathway from the retinohypothalamic tract. Pathway 2. Same wavelength entering the eye, a different system reading it, a different neural destination, a different autonomic output. The anatomy supports two hide. But here is where the evidence requires more care than the anatomy. Healthy subjects exposed to blue light showed suppressed vagal cardiac modulation, as Yuta and colleagues found at Nagoya City University, published in the Journal of Physiological Anthropology. The parasympathetic system decreased. The most directly relevant controlled measurement produced a result that directly contradicts the clinical tradition that blue perception calms. This contradiction is the strongest piece of counter-evidence in the literature, and it must sit in the open. What did Utah test? Direct blue LED illumination, raw photons at melanopsin's peak wavelength aimed at the retina at controlled intensity. A melanopsin input, pathway 1 isolated and measured. The study found pathway 1 doing what pathway 1 us, activating the sympathetic system through melanopsin's retinohypothalamic projection. The result confirms the melanopsin's mechanism, meaning the result does not test the perceptual mechanism. Physically, the difference between the two inputs is measurable. A blue LED aimed at the retina delivers a narrowband emission, a concentrated spike of photons at the activation wavelength, at an intensity sufficient to drive melanopsin. The photon flux is high in a narrow spectral window. The melanopsin cells receive maximal stimulation because the energy is concentrated precisely where their absorption curve peaks. Blue-tinted glasses deliver something fundamentally different, a broadband shift. Ambient room light containing all visible wavelengths at mixed intensities passes to a lens that increases the proportion of blue in the perceived visual field while leaving the absolute photon count at each wavelength largely unchanged. The total blue-weighted energy reaching melanopsin changes minimally, but the ratio of blue to other wavelengths in the visual field shifts dramatically, and the cones, which encode color through ratios rather than absolute counts, register a strong blue shift. The two inputs selectively activate different receptor populations because the two receptor populations read different properties of light. Whether the distinction explains the contradictory results has not been tested in a designed comparison. The anatomy supports two routes. The controlled measurement tested one. The clinical tradition observed through the other. The disambiguation remains unperformed. Well, the clinical tradition reaches back a century, long before melanopsin had a name. Blue and indigo light applied to patients produced measurable calming effects, lower pulse rate, improved digestion, reduced anxiety symptoms. Red light produced the opposite, increased alertness, elevated heart rate, sympathetic markers rising with red, parasympathetic markers rising with blue. The optometrist who documented these effects across decades of clinical practice, Harry Riley Spittler, developed an entire field around them. Syntonics, published in the Syntonic Principle in 1941, predated the discovery of melanopsin by 80 years. Spittler did not know about the retinohypothalamic tract. He did not know about the frechiasmatic nucleus. He observed that different colors of light applied through the eyes produced different and measurable autonomic effects, and he built a clinical practice around the observation. What that clinical tradition documented, modern neuroscience would later split across two pathways. Red light alertness maps onto the melanopsin system. Blue light calming maps onto the perceptual limbic pathway, the pathway melanopsin cannot explain because melanopsin produces the opposite autonomic response to blue. A century of clinical observation and thousands of patients, with optometric practitioners still using syntonics today. The mechanism was never formally identified because the discovery of melanopsin in 2002 appeared to explain every non-visual effect the eye produces, and the field stopped looking for a second pathway. Syntonics was filed under color therapy and dismissed. The logic required ignoring the observations that melanopsin's mechanism predicts wrong. Melanopsin predicts blue should activate the sympathetic system. A century of clinical record shows blue calming it. Either the records are systematically wrong across 100 years and thousands of independent clinical observations, or the single mechanism assumption is incomplete. The anatomy of the eye, with its two parallel networks projecting to different neural destinations, suggests incomplete. The dismissal was based on the assumption that one mechanism should explain everything, and the mechanism found appeared sufficient until the contradictions were examined. Evolutionary logic supports two systems. Melanopsin evolved to detect daylight for circadian timing, a function requiring measurement of raw photon energy without any need to identify what the light source is. The image-forming system evolved to construct a detailed visual representation for navigation, predator detection, food identification, requiring interpretation of what each wavelength means in the visual scene. Different computational tasks requiring different inputs. A system that times the body's clock needs to know how much blue-weighted light is present. A system that reads the environment needs to know what the visual field contains. The blue of water signaling proximity to a drinkable resource. The green of vegetation signaling edible territory. The red of blood or fire signaling threat or warmth. Each color carries survival information that the visual cortex extracts and the limbic system evaluates. The autonomic response to color is the downstream consequence of that evaluation, the nervous system adjusting its state based on what the environment contains, not just how bright it is. That two systems produce different autonomic responses to an identical wavelength is two ancient systems solving different survival problems through one organ. The radio analogy captures the principle, two receivers sharing one antenna, each tuned to a different property of the incoming signal. AM reads amplitude, FM reads frequency, and both produce different outputs from an identical broadcast. Melanopsin reads photon count while cones read wavelength ratios, both processing the same photons entering the pupil through two independent decoders. Can the two pathways be separated in a living nervous system, measured independently, tested against each other? Heart rate variability makes it testable. HRV measures something different from heart rate. Your heart rate might sit at 72 beats per minute, but the interval between each beat varies. 830 milliseconds, then 850, then 820, then 820, then 860. That variation reflects competing inputs from the sympathetic and parasympathetic branches, adjusting the sinoatrial node's firing rate, beat to beat. When the parasympathetic branch dominates, the variation widens, the vagal brake modulating each heartbeat with nuanced adjustments. When the sympathetic branch dominates, the variation narrows, the heart locking into a metronomic rhythm. Width of the variation is the autonomic signature. A smartwatch tracking HRV over a week reveals the pattern, high variability correlating with the mornings you felt calm and the evenings you fell asleep easily. Low variability correlating with the afternoons that felt pressurized and the nights you lay awake. Vagal compression at the jugular foramen, described in the forward head discussion, reduces this readout. The nerve carrying the parasympathetic signal forced through a structural bottleneck that weakens its transmission. Any parasympathetic signal the blue glasses may generate must travel through that vagal pathway to reach the heart. If the pathway is compressed at the skull base by sustained forward head loading, the signal arrives attenuated regardless of how strongly the perceptual input activated it. The glasses provide the input. Cervical posture determines whether the input arrives. The two discussions connect. The blue glasses generate a parasympathetic signal, and the forward head posture determines whether the signal reaches the organs that respond to it. $15.10 are all it requires. Sit in a quiet room and measure baseline HRV for 5 minutes. Put on blue-tinted sunglasses, simple blue lenses, not blue-blocking glasses which serve the opposite function. Sit for 10 to 15 minutes with the lenses on, breathing normally, no phone, no reading, no stimulation beyond the blue-shifted visual field. Measure HRV again. The comparison matters more than the absolute number. A baseline of 38 milliseconds, RMSSD climbing to 45 during the wearing period, is a 19% increase in vagal tone from a perceptual input alone. Colored perception filtered through glass panes produced measurable autonomic changes within 10 minutes, as Edelhauser and colleagues measured at the University of Witten-Herdecke, published in Evidence-Based Complementary and Alternative Medicine. Red filtered light shifted HRV toward sympathetic dominance. Blue results were less definitive, but the methodology demonstrates that color perception through filtered ambient light produces measurable autonomic changes through a pathway operating differently from raw wavelength exposure. The HRV readout from a single session with blue-tinted lenses tells you what no published trial has yet isolated. If HRV increases during the wearing period, the RMSSD value climbing and beat-to-beat variation widening, the perceptual pathway is operating in your specific nervous system. If it stays flat, the pathway may not be responding, or the vagal pathway may be too compressed to transmit the signal. If HRV decreases, matching Uta's finding, the melanopsin input from ambient light may be dominating the perceptual input. The measurement answers the personal question. One evening I tested my own autonomic response with a pair of blue sunglasses and a chest strap monitor. The data on my wrist settled the question before the literature could. The number moved. The debate became personal. Morning and daytime without stress, Melanopsin needs bright outdoor light. 10,000 lux minimum for robust circadian entrainment. No glasses of any kind. The morning belongs to the sun. Wearing blue-blocking glasses all day blocks the wavelength your circadian clock requires for daytime entrainment. The intervention designed for evening, worn at noon, prevents the signal that corrects the circadian drift, causing the sleep problem. The person who wears amber lenses from breakfast to bedtime is blocking pathway 1 during the hours it needs to be active and blocking it again during the hours it needs to be blocked. The timing determines everything: morning light unfiltered, evening light filtered. The glasses serve both pathways correctly only when worn at the right hour. During acute stress in daytime, the blue-tinted glasses hypothesis. 10 to 20 minutes of blue-filtered perception may activate the parasympathetic pathway through the geniculostriate limbic route. The evidence is emerging. The anatomy is consistent. The controlled disambiguation has not been performed. The HRV self-measurement makes the hypothesis personally testable. 10 minutes with no HRV shift means your nervous system did not respond. Useful information in itself. A measurable shift means you have a data point from your own autonomic system that no review article can override. Evening. After sunset, amber or red-tinted lenses blocking 90% or more of blue light. Evidence established through multiple randomized controlled trials with physiological endpoints. Blocking the emission band prevents melanopsin from receiving the daytime signal that screens and LEDs produce. Melatonin onset proceeds on schedule. Sleep architecture improves. Evidence calibration deserves explicit statement. Amber glasses at night rest on randomized controlled data with physiological endpoints measured under blinded conditions. Blue glasses during stress rest on a century of clinical observation, measurable HRV effects, and an anatomical pathway consistent with the observations, but the specific perceptual limbic mechanism has not been isolated in a design comparison. 2 glasses, 2 times of day, 2 pathways, 2 evidence levels. Amber is clinical grade, blue is hypothesis grade with a self-test built in. The distinction matters because it determines how you weigh the recommendation. Amber lenses after sunset carry comparable evidence weight as any well-tested intervention, multiple trials, controlled conditions, replicated results. Blue lenses during acute stress carry the weight of a plausible hypothesis supported by anatomy and clinical tradition, but awaiting the designed experiment that would confirm or refute it. The self-test fills the gap for the individual. The formal trial fills the gap for the field. Your eye carries 2 networks inside one organ, one reading raw photon energy and reporting to the master clock through a tract that bypasses vision entirely, the other reading color as perception and reporting to the limbic system through projections that modulate emotional state and autonomic tone. Blue light hits the first network and says, "Wake up." Blue perception hits the second and may say, "Calm down." Both networks operate simultaneously in every waking moment. Melanopsin responding to photon intensity while the cones respond to wavelength ratios, and the autonomic nervous system integrates both signals continuously. Your body state at any given moment reflects 2 independent inputs arriving through 2 independent neural destinations. Blue light from a screen at 11 p.m., melanopsin input, sympathetic activation, melatonin suppressed. Blue sky at 10 a.m., melanopsin input, circadian entrainment, the clock calibrated correctly. Blue-tinted glasses during an anxious afternoon, perceptual input, and the autonomic response, if the perceptual limbic pathway operates as anatomy and clinical tradition suggest, shifts toward parasympathetic. Back to the paradox from the opening. Blue light suppresses melatonin and shifts the nervous system toward sympathetic dominance. Blue glasses appear to shift it the other way. Both involve blue, both involve your eyes. Your retina carries 2 networks, one ancient, one even older, each reading identical photons through different physics. One measures energy, the other reads meaning. The paradox was the assumption that one organ could only listen one way. Your eye has 2 ways to listen, and the blue that enters it speaks to both.